Often when interpreting an observation of a random variable, we want to know where it stands with respect to the rest of the population. So we want some measure of relative standing, and one such measure is to count the number of standard deviations away from the mean of the population for our observation. So this is called a z-score. And we can calculate this by taking our observation, subtracting the average for the population, and dividing by the standard deviation for the population. And this is called the z-score, and you can see its formula is x, the observation, minus mu over sigma, where mu and sigma are the mean and standard deviation of the population, respectively. How can we use it? Well, one way we can use z-scores is perhaps for comparison of performance. And here's an example from football. We have the NFL Combine is a week-long showcase where college football players go to basically strut their stuff in front of coaches, managers, scouts, etc. And they have various tests. And we found some data combining the results of the tests for over 750 prospects over a 7-year period, from 2005 to 2011. And for the two tests, the 40-yard dash and the cone test, we had for wide receivers, the average on the 40-yard dash was 4.51, and that was the average time, 4.51 seconds, and the average time to complete the cone test was 6.96 seconds. And the standard deviation for the cone test for the wide receivers was 0.2, and the standard deviation for the 40-yard dash was 0.1. One of our own players from Notre Dame, Golden Tate, took part in the 2010 NFL Combine, and his results for the 40-yard dash were 4.42 seconds, and for the cone test his time was 7.12 seconds. So we might ask, in which test did he have a better performance? So in order to figure that out, we need to take into account the average for wide receivers. Golden Tate was a wide receiver for those particular tests, and the standard deviation. So we're going to compare the z-scores for both tests. So we calculate our observed values for Golden Tate's performance minus the mean over the standard deviation for both tests. So we get for the 40-yard dash, Golden Tate's z-score is 4.42, his observed time, minus the average for wide receivers, which is 4.51, divided by the standard deviation for the 40-yard dash, which is 0.1. So we see he was 0.9 standard deviations below the mean for that particular test. Now in this case, being below the mean is better than being above the mean because it's a timed test. Lower times are better. The z-score for the cone test was Golden Tate's time 7.12 minus the average 6.96 divided by the standard deviation for that test for wide receivers, which is 0.2, and that's 0.8 standard deviations above the mean. So his performance for the 40-yard dash was better in comparison to the population than his performance for the cone test. Another way we can use z-scores is to make better decisions about our problem in the last section, whether a string of baskets and misses was randomly generated or not. So our reasoning might go like this. If a player took k shots with a constant probability p of making a basket on every shot, where k is very large, we've already seen that the expected length of the longest run of baskets is approximately minus the natural log of 1 minus p times k over the natural log of p. Now we can also get a value for the standard deviation, and this is from Schilling's paper, which you can find a reference for in the notes. And the standard deviation for very large k, funnily enough, does not depend on k. It's approximately minus pi over the square root of 6 times the natural log of p. So the chances that the length of the longest run of baskets in a randomly generated sequence will be outside the interval from 2 standard deviations below the mean to 2 standard deviations above the mean is about 5%. Now this distribution, this density is not normal, but it's roughly normal. So that is still approximately 5%. If the longest run in the data is outside this interval, I might say, okay, that sequence is not randomly generated because it's too far away from what I might expect. And otherwise, I might say there's not enough evidence to say that the sequence is not randomly generated. If that's my decision rule, my way of deciding whether the sequence is randomly generated or not, there's a probability I might be making a mistake. The chances that it is a randomly generated sequence and I say it's not, the chances of making that type of mistake are 5%. Okay, this is a crude example of something called hypothesis testing, which you can explore in more detail if you take a statistics course. Let's see our crude example of hypothesis testing in action. Okay, let's look at an example, our last example from the last section. We looked at data for a string of 548 consecutive shots taken by Dion Waiters, and he has a career field goal percentage of 0.417. So using that as P, we want to check if the sequence we had was randomly generated or not. Was a sequence of Bernoulli trials with constant P or something else? So we saw that the longest run of baskets in the data had length 5. In fact, there were 3 such runs. And in this experiment, we also calculated what we might expect for the length of the longest run in the data. The expected value, or the expected length of the longest run of baskets in the data was minus the natural log of 1 minus p times k over the natural log of p, and that was approximately 7, or approximately 6.88. Now the standard deviation, according to our formula, is minus pi over the square root of 6 times the natural log of p, and that's approximately 1.47. So our rule is that if our observation of the length of the longest run, which is 5 in this case, is more than 2 standard deviations away from what we might expect, then we're going to say that we think that this sequence was not randomly generated. Otherwise, we're going to say there's insufficient evidence to suggest that it's not randomly generated. Well, the interval from the mean minus 2 standard deviations to the mean plus 2 standard deviations is from 3.74 to 9.62. Our observed longest run is 5, which is certainly within that interval, so we don't decide that this sequence was not randomly generated. Instead, we say we don't have sufficient evidence to conclude that the sequence was not randomly generated or was not a result of 548 Bernoulli trials with the probability of success equal to 0.417. In other words, we're saying that we really don't think that we don't have sufficient evidence to say that this is a streaky player or that this is a result of streaky play.